Okay, so let us continue with uniform leaky wave antenna. Now, how to fit this antenna structure? We have two open end, left hand side and right hand side. So, usually we place our source here on left hand side, and then right hand side it will be mesh terminated. Now, I want maximum power, it should come out as radiation. Then we have to control alpha or length of the antenna depending on the requirements, because if I consider, let us say, at least 90% power should comes out as radiation, so that minimum power is lost to my mesh termination. What we can do, for a given length, either we have to increase alpha by controlling the width of the slot or the position of the slot, or for a given constant alpha we have to increase the length of the antenna, so that at least 90% power is radiated. Now, the beam width, it depends on alpha. So, depending on application requirements, we have to choose a proper alpha value and the length of the antenna. In this case, we are having one single beam. We can also generate dual beam, sometimes used for imaging applications. So, in this case, we have to place the source at midpoint and left and rightmost end will be mesh terminated. We will be having symmetrically placed, will be having two beams symmetrically placed at theta equal to plus minus theta m. And now, we have to satisfy one condition to obtain these dual beams. It can be shown that location of main beam maxima for beta greater than alpha, if beta less than alpha, in that case we will be having only one beam. So, the condition to obtain two beams is beta greater than alpha, and in that case the beam direction theta naught, it is being measured from the guiding structure itself. It can be given by cos square theta naught equal to beta by k naught whole square minus alpha by k naught whole square. Now, beam width, it changes with frequency, because alpha changes with frequency. A typical alpha by k naught plot for a given structure, you see alpha by k naught, it is highest at the lowest frequency, then it decreases. So, if alpha changes with frequency, the problem we will be facing that beam width, it will also change with frequency. So, this is a problem with this type of antennas. We will be having narrowest beam width, a fan beam like structure, since we are using one dimensional structure, at beta equal to 0.518 alpha value. For a given structure, then we can plot beta by k naught and alpha by k naught, and from that we can actually show in which region we will be expecting these dual beams and for which value we will be having the narrowest beam width. So, depending on application, then we can choose the dimension. This is one interesting example of uniform leaky wave antenna, where we can vary both beta and alpha of the structure. It is nothing but one SIW structure, substrate integrated rectangular waveguide structure, the middle part, and you can identify the feed line. We are using microstrip feed line to excite the SIW structure. Now, let me draw the field diagram for SIW structure. If I consider a cross sectional view of closed SIW structure which is supporting TE10 mode, we have electric field maxima on the central plane, and then it decreases left and right hand side. It is a guided wave mode. So, if you remember, for SIW structure we have periodic vias here. We have to maintain a spacing given by the relationships which we already learned, to minimize the leakage loss from the side walls. So, we can control then leakage by changing the pitch of this via. We can intentionally have some leakage coming out from the side walls by controlling the via pitch, and that is how we can design a leaky wave antenna from SIW structure itself. Another possible scenario, we see on the mid plane electric field is parallel to mid plane. So, that means we can place one magnetic wall here or open circuit here, even then it should support wave guiding mode, or it will work as a guiding structure. So, using that concept, if I cut this structure from midpoint, then it looks like half of the SIW structure. We call it half mode SIW structure, and it will also support wave propagation almost without any leakage. But if I terminate my dielectric here on the central plane, we are expecting highest electric field, and then left hand side it will decrease. And if I terminate the structure on this plane, we have dielectric air boundary, this side air, left hand side let us say we have some epsilon r, and we are having some fringing field. But for this fringing field, electric field and magnetic field, they will be in phase quadrature. We do not have as such any radiation from this. Let me plot the field strength along the line. It is 0 electric field strength, and then we are having maximum on the mid plane. For rectangular waveguide also we can plot the same thing. Now, let us consider one scenario where we are having a half mode like SIW structure, but the width is little more than lambda g by 4. So, this is the required structure for half mode SIW. Now, it is more than that value, or maybe another scenario, in this case it is little less than the required lambda g by 4. So, in both of these two cases we will be having leakage, and not only that, you recall that beta of any given rectangular waveguide, it depends on the width of the structure, right. So, if I change frequency for a given structure, beta will change, or in other words, at a given frequency if I change W, then beta will change. So, beta it becomes a function of the width of a rectangular waveguide. For this type of structure also we can control beta by changing the width of the structure. So, we may have a structure where we can control both alpha and beta. How? We can use this W variation to control beta, that means to control the beam direction theta m, and also we can control leakage by changing the periodicity in this structure. That is how we can control the beam width of the structure. Here is the example. So, left hand side it is showing a TE10 like mode, but in this case on left and right hand side they are using PMC open circuit condition just opposite to SIW side walls, and the middle example is a half mode SIW structure. Now, we have something in between. We can control W to change beta, and you can see for this left hand side chain of vias, they are changing the pitch using wider pitch, so that we have some leakage from this. And for this structure, if we plot the electric field, it looks like this. Inside the guiding structure we have TE10 like mode, but outside this we have we have some extension here. We have a parallel plate like mode and then fringing field in airs, and for this we have electric field and magnetic field in same phase, we have radiation from this. So, we can control beta by controlling W, and we can control alpha by controlling P. Here is a plot. In the first plot, theta rad, so nothing but this theta m, how it changes with periodicity P. So, we are changing periodicity P, and you recall that the effective width of one SIW structure, it depends on the via to via separation also, pitch. So, if I change P, beta will also change at the same time. So, this is a plot of theta rad, it is obtained by using this relationship sin inverse beta by k naught, sorry. So, this theta rad they are using, they are calculating it from sin inverse beta by k naught, that is how they are plotting. And then in the next plot, it is alpha by k naught versus P. So, when P increases, alpha or leakage loss it increases. We can control then both beta and alpha. These are some fabricated example. In the first example, delta theta, half power beam width is 5 degree, second example 10 degree. Now, theta rad, for the first example it is placed at some given frequency, the beam is placed at 30 degree, in the second example it is at 50 degree. It is also possible that for the same theta rad they are changing the beam width to 10 degree. In the first example it was 5 degree, in the third example it is changed to 10 degree. Now, for the first and third example, obviously we have different alpha value. So, to radiate at least 90% power, you see the length of these two structures, they are different. In the first example we have smaller alpha, in the third example we have higher alpha. So, we can control both alpha and beta. So, that is how for any given application we can fix theta rad as well as we can fix the beam width of the antenna. This is another example of uniform leaky wave antenna, but in this case it is designed in for SINRD line. So, this is you can see the SINRD channel inside here shown by this white line here, and over this they are using a brass plate. On the brass plate you can see the slot, almost similar physics like a rectangular waveguide. This is designed for 90 gigahertz band. In the first figure it is showing beam direction versus frequency. So, if we change frequency, beam direction is changing, and theta m beam direction it is given by sin inverse beta by k naught. Here is the measured and simulated radiation pattern at a given frequency 92 gigahertz in H plane and E plane. Next topic is periodic leaky wave antenna. So, as we discussed, the structure itself will support slow wave mode, but since we have periodic structure, we can use flow K mode analysis, and we can see if we analyze this structure, there are infinite modes possible. These are called the space harmonics, and at least one of these space harmonics should be leaky wave mode, that means first wave mode, and the radiation will come from that particular mode only, and it becomes a function of the periodicity as well as the frequency, operating frequency. So, let us see how alpha, beta and the radiation angle it depends, they are related. So, in general let us say x directed wave number is given as kx m, we are considering a periodic structure, it is equal to kx naught plus twice pi m by d. So, beta this is equal to beta minus j alpha plus twice pi m by d, and we can consider beta. You see it's having one dominant mode component, this beta, and this is due to all the periodic modes. So, for m equal to 0, plus minus 1, plus minus 2, we have different modes and we have infinite number of modes. So, the resultant mode kxm, it is the summation of this overall beta. In general, we are writing down then this is equal to beta m minus j alpha. For leaky wave beam, beta by k naught or beta m by k naught, it should be less than 1. Let us say we are considering the mth mode is radiating. M can be any integer, positive or negative, and the mth mode is radiating. Then for this mth mode, it should be first wave, otherwise no radiation will come from this. So, beta m by k naught, it should be then less than 1, and you recall k naught equal to twice pi by lambda naught in free space. Now, for small alpha, leakage is small, so kx naught is almost real. Now, for mth leaky wave beam, how we are measuring theta m, just like the previous figure, we are measuring theta m from the broadside direction. So, only thing is that we have a periodic structure here instead of that uniform structure. So, in that case, theta m, we have similar relationship, sin inverse beta by k naught, but instead of beta, now we have beta m, that means beta plus twice m pi by d by k naught, where you see m, it can be 0, it can be plus minus 1, plus minus 2, anything. So, m equal to 0, that represents the dominant mode. Obviously, it will be a slow wave, it will not radiate. Now, radiation, it can come only if m takes negative values. We may have radiation from m equal to minus 1 mode, we may have radiation from m equal to minus 2 mode. So, let us consider the fundamental mode, just after m equal to 0, m equal to minus 1 harmonic, it is radiating. So, if I start from cutoff frequency and keep on increasing the frequency, the mode that first radiate is m equal to minus 1 mode. Now, let us put m equal to minus here, minus 1 here, and you remember d is the periodicity. In this case, d we are representing the periodicity, the separation between two perturbation. Then if I put m equal to minus 1, then it becomes sin inverse beta minus twice pi by d by k naught. Now, we are expressing it in terms of lambda. So, theta m for m equal to minus 1, this is sin inverse beta by k naught, we are taking beta common. So, we should multiply it this factor by 1 by beta, 2 pi by lambda. So, we have then 1 minus lambda by d. Now, you see for beta by k naught, it should be, or overall beta m by k naught, it should be less than 1. That means lambda naught by lambda into 1 minus lambda by d, it should be less than 1. So, if I start from cutoff frequency, then the radiation, it will, where it will start, the first value it takes minus 1 when lambda is when d is lambda by 2. If I consider the periodicity, that is equal to lambda by 2 at the starting frequency. So, it is taking minus 1 and radiation will start at theta m equal to minus 90 degree. So, if I go back to this figure, if I keep on increasing the frequency from the cutoff frequency, then radiation will start in opposite direction in the feeding end, and then if I increase frequency further, theta m will decrease, and finally at a value when theta m equal to 0, the radiation will be in broadside direction here. If we further increase the frequency, it will enter the first quadrant and the radiation it will continue in the first quadrant, but the scanning it is limited by the second harmonics. So, let me draw better this diagram. Let us say we have the wave guiding structure, I am showing it by one line, and now this is the broadside direction. So, when d equal to lambda by 2, then theta m this is equal to minus 90 degree, we have radiation in this direction. If I increase frequency, then main beam direction it will change and theta m decreases. If I keep on increasing the frequency, at this point when theta m equal to 0, so in that case d equal to, from the expression we can see it is equal to lambda. After that, if we keep on increasing the main beam, it will now will be in first quadrant. But the problem is that at some value, let us say when the main beam is at plus 20 degree or theta m equal to plus 20 degree, in that case a second beam will appear for which m equal to minus 2. Now, if I keep on increasing the frequency further, we will not be having one single beam, we will have a second beam that is appearing from here and it will follow similar characteristics. Then the maximum scan angle it is determined by the emergence of the second beam, and if I compare the scanning characteristics with the previous one, what we can see, for periodic leaky wave antenna it can scan both the quadrant, first quadrant and the second quadrant, but in this case also we have the similar problem in broadside direction. We can't achieve radiation in broadside direction. Why? Here also when d equal to lambda, in that case the input impedance it becomes either infinite or 0, and the waveguide it will not accept any power because of the impedance mismatch, and we won't be having any radiation in broadside direction. So, for both conventional uniform leaky wave antenna and periodic leaky wave antenna, we do not have any radiation in broadside direction. Now, I am going to show you some examples. This is a periodic leaky wave antenna designed in SIW technology by us. You can see the mid part is the SIW structure, left hand and right hand side we have microstrip feed line, and left hand side if I place the power source on left hand side, then right hand side should be mass terminated. Here we are using 50 ohm microstrip line, so we have to use 150 ohm load here. Now, the perturbation we are etching some slot as perturbation, and the radiation or leakage it will come out from the slot. We may have different shape of the slot. So, basically what we tried in this study, that we used different shape of the slots and studied their radiation characteristics. Now, the periodicity, this is the pitch, the separation between these two, and this periodicity P determines the operation. As you in the previous one, actually we are representing periodicity by D here. Now, look at the input impedance plot. When it is, we can, if I follow any one of this line, let us say this red line which is for elliptical shape of the slot, at 8 gigahertz this beam will appear to my left, because I am feeding from the left hand side, where theta m is approximately minus 90 degree. This is for the m equal to minus 1. Now, if I keep on increasing the frequency, we are having good matching level, till 11 gigahertz or 11.5 gigahertz, and the beam, it will continuously change its location, it will come to near broadside direction, and you can see at 12 gigahertz we have a stop band. Input impedance is becoming infinite. With this waveguide no longer accept any power, and we do not have any radiation, it is shown by this red circle. Now, if I continue increasing frequency, then again we have radiation from this upper band. In this part, this beam will enter the first quadrant, and we have radiation in forward quadrant. So, for pure series element, impedance seen at the elements is open circuited at this stop band frequency, and for pure shunt element, impedance seen at the elements is short circuited. So, by using just series element or short element, we can't avoid this problem. So, that means we will be always facing the broad stop band at broadside direction, this problem. Very recently, this problem has been overcome by using both series and shunt element. In that case, they can cancel each other's effect, and the input impedance it can be then controlled by using both series and shunt element, and in that case it will accept power again, and we will be having radiation in broadside direction. I am showing one second example here. Periodic slot, this is edged on a SIW structure, but this is a rectangular slot. The periodicity is given by P and the length is L. So, you remember this is not a resonating slot, we are using these slots for leakage, and this is the beta by K naught plot. So, beta by K naught, since we have dielectric loaded structure, it is crossing 1 at some point, and for the first part, when beta by K naught is less than 1, itself it can behave as one uniform leaky wave antenna. If the periodicity P is very small, in that case we can consider it as one almost uniform perturbation along the length, if this P is much less than lambda. So, what is the conclusion for this type of structure? Using this type of periodicity, we can design both uniform leaky wave antenna and periodic leaky wave antenna. For periodic leaky wave antenna, the P periodicity, it should be lambda by 2 to lambda maximum, and if we focus on uniform leaky wave antenna, in that case the periodicity it should be much less compared to lambda, so that we can replace it by effectively one PRS layer, PRS structure, and we can call it one quasi uniform leaky wave antenna, since we do not have a continuous slot along the line. So, both scenario is possible. When we use it as a quasi uniform antenna, in that case we have to use beta by K naught less than 1, and when we use it as a periodic leaky wave antenna, in that case we have to use the right hand side, because the original guiding mode, in that case it should be a slow wave mode, and we are expecting radiation only from the higher order modes, m equal to -1 or m equal to -2 for those cases. So, this is one example of such uniform leaky wave antenna. You can see they are using different sizes of the slots. This is for impedance matching purpose. So, for the leaky wave antenna, then what we see, feeding is very simple. It can be excited by simply microstrip line or any 50 ohm line. Next day we will be discussing on transition, and not only that, we can also obtain scanning simply by frequency sweep, and for scanning purpose The preferred antenna type is periodic leaky wave antenna, since it can scan both the backward side and forward side. So, that is all on leaky wave antenna. Next, we will continue with the millimeter wave components. Thank you.